Radio direction finding. Radio direction finding was once the primary aviation navigational aid. It requires an antenna that is directional, more sensitive in certain directions than in others. By combining the direction information from two or more suitably spaced receivers, the source of a transmission may be located in space via triangulation. Let us first consider the history of RDF. The earliest experiments in RDF were carried out in 1888 when Heinrich Hertz discovered the directional property of radio waves. Antennas with directional qualities will enhance field strength of the wanted signal and suppress, in the best case, unwanted signals from different directions. Hertz experimented on the directionality of open-loop wire as an antenna. When the antenna was aligned so it pointed at a signal, it produced maximum gain and produced zero signal when face on. This meant there was always an ambiguity in the location of a signal. It would produce the same output if the signal was in front or back of the antenna. Later experiments also used dipole antennas, which work in the opposite sense, reaching maximum gain at right angles and zero when aligned. The triumphant advance of RDF in all aspects was brought by World War I and World War II when the military users recognized the value of additional tactical and strategical information. RDF is part of passive electronic warfare. For the military, RDF systems are a key component of signals, intelligence systems, and methodologies. The target station tries to radiate the information in a narrow beam to its addressee, thus avoiding detection by RDF. The ability to locate the position of an enemy broadcaster has been invaluable since World War I and played a key role in the World War II's Battle of the Atlantic. RDF is used in the aviation of aircrafts and ships to locate emergency transmitters for search and rescue, for tracking wildlife, and to locate illegal or interfering transmitters. Radio direction finding systems. Number 1, Star RDF. Star RDF consists of cross-loop antenna and goniometer in the receiver. Consisted of 48 long wires and 60 meters length in a star-shaped array. A loop goniometer scanned the individual antennas for maximum signal. Bellini-Tosi goniometer. A key improvement in the RDF concept was introduced by two Italian officers, Ettore Bellini and Alessandro Tosi in 1909. During their experiments in 1907, Bellini and Tosi noticed that they could cause the received signal to be re-radiated by forming a loop with multiple winds of wire. The signals from the antennas were sent into coils wrapped around a wooden frame where the signals were recreated in the antenna between the coils. A separate loop antenna located in the area could then be used to hunt for direction without moving the main antennas. Early RDF systems were used largely for long-wave signals. These signals are able to travel very long distances, which made them useful for long-range navigation or LORAN stations. However, when the same technique was being applied to higher frequencies, unexpected difficulties arose due to the reflection of high-frequency signals from the ionosphere. The RDF station might now receive the same signal from two or more locations, especially during the day, which caused serious problems trying to determine the location. This led to the 1919 introduction of the ADCAC antenna. ADCAC antenna is an antenna array consisting of four equidistant vertical elements which can be used to transmit or receive directional radio waves. Two opposite antennas deliver a signal from their direction. Obviously, more antenna pairs yield stronger signals and higher accuracy. The Adcock array was invented by British engineer Frank Adcock in 1919 and has been used for a variety of applications, both civilian and military ever since. Although originally conceived for receiving low-frequency waves, it has also been used for transmitting and has since been adapted for use at much higher frequencies, up to UHF. In the early 1930s, the ADCAC antenna became a key feature of the newly created radio navigation system for aviation, the Low Frequency Radio Range or LFR network, which consisted of hundreds of ADCAC antenna arrays, defined the airways used by aircraft for instrument flying. The LFR remained as the main aerial navigation technology until it was replaced by the VOR system in the 1950s and 60s. The ADCAC antenna array has been widely used commercially and implemented in vertical antenna heights ranging from over 130 feet in the LFR network to as small as 5 inches in the tactical direction finding applications. Automated RDF or Automated Radio Direction Finding System. The system was intended for the wearing of aircraft via 2 to 6 frequency channels. It consists of processing rack, antenna system, antenna with a test generator, remote control equipment, and a shelter with a life support system. It was designed on a modular principle which allows creating an optimum configuration. The third method is the Doppler RDF. The Doppler shift or Doppler effect is named after Christian Doppler, who described it in 1842. Doppler shift is a type of frequency modulation. Imagine we have a single antenna mounted on a rotating disc. As this disc is rotated, the antenna will move closer and then further away from the transmitter. At positions A and C, the antenna is stationary relative to the transmitter, so Doppler shift is 0. At position B, moving away, and D, moving towards, Doppler shift will be maximum. Continuous measurements of Doppler shift will yield a so-called Doppler sine wave. To sum it up, relative motion of objects towards each other causes the observed frequency to increase. Relative motion away from each other causes a decrease in frequency. Doppler RDF systems use circularly arranged vertical dipoles which are scanned. After each scanning cycle, a few milliseconds, the difference in frequency between the individual antennas or Doppler effect allows the calculation for the direction of the radiation source. Highly accurate direction finding systems. Single channel direction finding refers to the use of a multi-antenna array with a single channel radio receiver. This approach to direction finding offers some advantages and drawbacks. It only uses one receiver. Advantage, mobility, and lower power consumption. Disadvantage, it does not have the ability to look at each antenna simultaneously. More complex operations need to occur at the antenna in order to present the signal to the receiver. Pseudo-Doppler direction finding technique or pseudo-Doppler DF technique. During the war, to replace radiogoniometers in the intelligence gathering role, reducing the time needed to take an accurate fix from minutes to seconds. The ability to inexpensively process radio signals using microcontrollers allowed pseudo-Doppler direction finders to take over most of the radiogoniometers' remaining roles from the 1980s. Pseudo-Doppler direction finding technique is a phase-based direction finding method that produces a bearing estimate on the received signal by measuring the Doppler shift induced on the signal by sampling around the elements of a circular array. The original method used a single antenna that physically moved into a circle but the modern approach uses a multi-antenna circular array with each antenna sampled in succession. Another method is the Watson-Watt ADCAC antenna array. Originally developed shortly after World War I and named after Sir Robert Alexander Watson Watt, one of the inventors of radar, Watson Watt is an amplitude comparison direction finding system. It uses two pairs of ADCAC antennas to compare the level of the signal received at each antenna. The two of the pairs are collocated but perpendicularly oriented to produce what can be referred to as the NS north-south and EW east-west signals that will then be passed to the receiver. The receiver then computes varying angle by taking the arctangent of the ratio of the NS and EW signal. The last technique used for highly accurate direction finding systems is correlative interferometer. The basic principle consists in comparing the measured phase differences with the phase differences obtained for a direction finding antenna system of known configuration at a known wave angle or reference dataset. The comparison is made for different azimuth values of the reference dataset. The bearing is obtained from the data for which the correlation coefficient is at a maximum. In case the direction-finding antenna elements have directional antenna pattern, the amplitude may be included in the comparison.